Maybe it's working now, I hope. Let's see. Just want to remind you, there's no class on Monday due to July 4th. We have a quiz at the end over 6.1 through 6.3. We said, are there any questions for the quiz you want to look at? And then also we can look at any homework questions you have. Okay. Anything you'd like to look at whatsoever?
If we look at 6.6b, I think we did A yesterday.
All right, so, oh yeah, we didn't do one that was exactly like this. That's a good point, because we actually didn't cover this. 6.1, 6B, sometimes I skip over a little bit of stuff for lack of time. It says this, sketch the graph of y equals x sine x. And then verbalize how the graph varies from the graph of sine x. I'll just say, discuss its relation to just the sine function. This is kind of an interesting question for science majors. How can I sketch that? Here's what people do in their applied classes, is they'll say, well, wait a minute, this looks like y equals x multiplied by an oscillating function sine x that goes up and down between plus and minus 1. That has period 2 pi, right? Because sine has period 2 pi. And so what you do is you draw the line y equals x and the line y equals minus x. And as sine goes between plus and minus 1, the graph will go between x times plus and minus 1. And furthermore, sine starts at 0, so you start at this point here, right? If you plug in x equals 0, you can think of that as plugging in a point. 0 times sine 0 is 0, and that's the y value at 0. So you get the point 0, 0 by plugging in. And then sine gradually becomes positive until it's 1. And so you go something like this. And then it oscillates down to minus 1. And then you're at y equals minus x when this is y equals minus x. I didn't draw it properly. And then it goes back plus x when it's 1 and back down to minus x. And it just oscillates back and forth between these two. Maybe you draw them dotted just to make sure, to show people that's not the graph of a function you're sketching. So here you draw the lines y equals x and y equals minus x and make this curve oscillate up and down between the two, starting at 0, 0 and going positive. And what happens is sine completes one period and is back to 0 again at 2 pi. So this is 2 pi here, when it's gone up to the top once and down to the bottom once and back to the middle. And if you keep sketching this, it will come back and cross it here again at 4 pi, oops, 2 pi units later, because right, sine has gone one more period and oscillates you between plus and minus x one more time. So that's what it is. You get a graph like this and you say, it looks like this, same period as sine x. So here's the description. That's what they want you to do on this one. There's also the other one, g of x equals x plus sine x. Well, I have g of x equals x plus sine x. How do I do that? You can look at the back and kind of tell how to sketch this. And what you can do is plot the two of them, plot y equals sine x. I know what that looks like. It goes up and down between plus and minus 1. With period 2 pi, so there's 2 pi there and there's 4 pi there. And now y equals x, I know what that looks like. That's the line, right? Y equals x splits the axis, just like I drew it here. Right, when x equals 2 pi, y equals 2 pi, for instance. There's pi. Ooh. That's too close to 1, isn't it? Oh, golly. It's hard to draw this the right scale, but the other thing is it turns out from calculus, we don't tell you this yet, but sine starts out as just tangent to this line y equals x. So it looks like that. So there's pi and there's 2 pi. All right, and so what happens is when you add these two together, really talking here, Joey. You can stack them on top of each other. You can say, well, I guess this would be, oh. It was all yellow on the outside. All right, so this is pi over 2 and sine is equal to 1, right? And so this must be pi over 2 here. But you'll take sine, when x is pi over 2, sine is 1. And this is the line y equals x goes through 1. And so you add them together, you take this, it goes through, sine y equals x goes through pi over 2. And so you take 1 and stack it on top of here and get to this point 1 plus pi over 2, the sum of the two y coordinates. And so what you got is something that looks like this. And then this one starts going down gradually. And when it's equal to 0, you're going to cross here because you're going to add 0 to the line y equals x. When this gets down to minus 1, you're adding minus 1 to the line y equals x. So this is minus 1 here at what, 3 pi over 2. And so you'll get back down to the bottom point, 3 pi over 2 minus 1. And then it will come back here. When this is 0, it'll be back to 0. So this will be 2 pi, it'll go right through there again. And this will be the point pi, because you're adding 0 when x is pi. So it will go back, it'll just oscillate up and down kind of like that, around the line y equals x. So that was some graphing things that are occasionally useful in your science classes. Just take the one y coordinates and stack it on top of the other one. This one's negative, down. When this is positive, you stack it on top. This is negative, you go down. This is positive, you stack it up. Any other questions? That's a good one. Can you make sketches of the sine and cosine graphs and tangent and all 6 trig functions? And can you see a graph and figure out the equation that goes with it? Evaluate your trig functions. You got a hard problem where you take a trig function, inverse trig function, right? All right, how about last time? Was there any questions on last time that you wanted to look at? That's one of the hardest sections of the semester. Difficult trig equations. All right, well, I'm gonna do the next section then. This one is not too bad. Section 7.1. Again, we skipped 7.1 through 7.4. Went on to 7.5, and we're gonna come back to this. 7.1 is on simplifying trigonometric expressions. You'd be surprised how many times in your classes to come, those of you that take some science or engineering, of course, you get this complicated trigonometry expression and it simplifies down to something really easy. It's just amazing. You want to do that, right? Once you see it, it's simply, a lot of times you can graph it, for instance, you know, what its behavior is. And so for these, we need to recall all the identities we've done, because one of the big deals is to use identities to solve these. We need to recall, I think I can just give a list of them here. Don't think I put the list for the semester up there, but probably what I should do now is put up the list of formulas for the semester on T2L, and you can take a look at those. And when you do these problems, you might want to just look at those and say, oh yeah, these are the ones I should know. Because in the next week, we're going to go through some new trig formulas, and when we're done with those, we'll have pretty much all the trig identities we need for the semester. All the identity, well, we're done with trigonometry. But for these, we need to recall things like this. The secant of theta is 1 over the cosine of theta. The cosecant of theta, 1 over the sine of theta. The cotangent of theta is 1 over the tangent of theta. And you want to know the other threes in reverse also. You want to be able to say tangent is 1 over cotangent. Maybe I should write that down. I hate to write them both down sometimes, but cosine correspondingly is 1 over secant. We call them identities again because they're true whenever everything's defined. There are places where secant isn't defined, right? It's got asymptotes, but cosine is, and in that case, you can't say something equals not something. But wherever they're both defined, these are true, so we call them identities. And sine theta correspondingly is 1 over cosecant theta. Tangent theta, 1 over cotangent theta. All right, so those are the reciprocal identities. And then we have the Pythagorean identities are very important, right? We know that sine squared plus cosine squared equals 1. Part of this is just a review and make these things really sink in, because you use these again in calculus. If you take calculus after this, you really need all of these. Very important. So sine squared plus cosine squared equals 1. And it's called the Pythagorean identity, recall, because on the unit circle, you took an angle, theta, and drew this little triangle like this. Well, this side is cosine theta. This side is sine theta. And if you root sum square them, you're supposed to get 1 because it's a unit circle. Cosine squared plus sine squared equals 1 by the 1 squared by the Pythagorean theorem. So this is just the Pythagorean theorem applied to this little triangle that's in the unit circle, if you recall. And then what can you do to get the other two Pythagorean identities? I'm trying to give you here some ideas to be able to memorize these for later. How do you memorize the other two easily? Remember? If you divide this equation through by cosine squared, what do you get? Sine squared over cosine squared is tangent squared, right? If I divide this by cosine squared. Cosine squared over cosine squared is 1. And 1 over cosine squared is secant squared. So I divide this through, I'm just imagining in my mind, I hope you can picture this, dividing each of these by cosine squared, and this is what I get, right? So if you can memorize this one on the test, you can figure this one out. Sometimes I used to forget these harder ones, right? And then if you divide this through by sine squared, divide sine squared by sine squared, you get 1. Divide cosine squared by sine squared, well, that's cotangent squared by the reciprocal identity. And 1 over sine squared is cosecant squared. That's the other one. So this one you can use to figure out these. That's why they write on this one tangent squared plus 1, but this one 1 plus cotangent squared. Why would they write them in reverse order? It's because you're thinking of dividing this by cosine squared, 1 here, but you divide this by sine squared, you get 1 here. So this is the easier way to memorize them if you're thinking of dividing through like that. So that's a nice way to remember those. You remember one and you can get them all, right? One ring to rule them all, and the Lord of the Rings. And then these are not so bad because you know the first 3, the other 3 are just turn those upside down, right? So those aren't too bad. Then we have the quotient identities, which I alluded to here. We were using them, right? Quotient identities say what? Each one of these or the tangent and cotangent is the quotient of the sine and cosine. We call the tangent theta the sine theta over cosine theta. And cotangent theta is cosine theta over sine theta. Now that we've done triangles, we can figure these out easier than we did in the beginning if you forget these, right? If you look at this, remember tangent in a triangle is opposite over adjacent. Oh, that's sine over cosine. Cotangent is adjacent over opposite. Oh, that's cosine over sine. So if you figure it out, if you forget it, you can figure it out from this triangle. That's why this triangle diagram is really nice. It helps you to figure out these quotient identities. It also helps you to figure out some of these others sometimes if you, anyway, so we can figure those out from this little triangle here, and we can figure these out by dividing through. Then we have these identities. Remember that every trig function is either even or odd. What's the sine of minus theta? Oh, it's the minus the sine of theta. Sine is an odd function, we said, because the minus comes out. We proved that on the unit circle again. You don't have to memorize the proof. Most people just remember sine is odd. Cosine, however, is an even function. Cosine of minus theta is cosine plus theta. The minus goes away. Those are the even and odd identities. Put that on the side, even / odd identities. Actually, this one's odd and this one's even. This is the name of the group. Put it here so I don't look like I'm labeling those. Even odd identities. And now, what about the other four? You remember which ones are even and which ones are odd? You know how I often remember these, so that I have trouble ever? Tangent of minus theta, was that even or odd? If I remember, it's sine of theta. Tangent is sine over cosine. So tangent of minus theta is sine of minus theta over cosine minus theta. On sine, the minus comes out. Cosine, the minus goes away. Oh, that's minus the tangent of theta. So if you forget it, you can figure it out. A nice way to remember these from algebra is when you have an odd divided by an even, the minus comes out here and not here. You always get an odd function. So an odd function divided by an even is always odd. The minus comes out. An even over an even is even, and odd over an odd is even because the minuses cancel. And so those kind of even and odd things you learn from algebra come in real handy here, because once you know sine and cosine, you know the other four immediately. I'll erase this derivation here and just say this is minus the tangent of theta. Tangent is an odd function. And then the other three are reciprocals. The reciprocal of an odd function is odd, right? Cosecant of minus theta. The minus comes out. And you can figure out how to prove that, right? Cosecant of minus theta is 1 over sine of minus theta. Is 1 over minus the sine of theta, because sine is odd. Oh, that's minus the cosecant of theta, right? Because so once you know these first two, sine is odd and cosine is even, the others you can figure out from these quotient and reciprocal identities if you need to, right? Tangent, you write it as sine over cosine, odd over even is odd. So I'm trying to give you some ideas how to memorize these better. And that's part of the purpose of the section, not just to learn how to simplify trig expressions, but to be able to memorize these things better. All right. And now, again, if cosine is even, then its reciprocal is even for the same reason as this one, right? If I take 1 over cosine minus theta, the minus won't come out, and I just get secant back. So secant of minus theta is secant of plus theta. And cotangent of minus theta being even over odd is minus cotangent of theta. So there's the even odd identities. And strangely enough, I always thought even and odd numbers come in pairs. Maybe these should come in pairs. No, they don't. 4 of them are odd, 2 of them are even. The way I remember it is cosine and its reciprocal are even. Everything else is odd. That helps me. But if I forget, I can figure it out from these two. Right? Need to know all those identities. Let's see. We got anything else there? Trying to think if I've left anything out. That's all we have so far. All right, so now we can use these to simplify trigonometric expressions. by the following rules of thumb. This is not the only way you do it. These are the common ways everybody knows. Think of these as rules of thumb. Here's how you try it. You first use algebra. I told you you're going to learn your algebra in this class, right? It's particularly regarding quotients and products. If you have a sum of quotients, you might try and put them over a common denominator. If you have a quotient with common factors, you cancel common factors, right, in quotients. So cancel common factors and quotients. This now your quotients will contain trig functions. That's the only difference. Before they contain like x, and you cancel x. Now we'll cancel trig functions. Cancel common trig functions and quotients. Put sums of quotients over common denominator. Sums are differences over a common denominator. It's just now there's sums of difference, so it'll be a trig functions. I'll abbreviate denominator here at the bottom of the quotient. And other things too. You eliminate compound quotients, right? If you have A over B over C over D, you call that a compound quotient. Now here we'll have trig functions in A, B, C, D. But what do you do with this? You rewrite this as A times D over B times C, right? Top times bottom over middle times middle, we said. So eliminate these compound quotients if you have a quotient of a quotient. All those things you did in algebra, mostly with quotients. So I'll put etc. because this is not exhaustive, but those are the main ones, all right? That's part A. The first thing you do, I hate to erase these, but I have to. Hopefully you sear these into your brains now so you can remember these when we need them. I'm sorry, I got a certain amount of board space and that's it. All right, so let's try that. And now B, you apply these trig identities that we have. That's not exhaustive either because we're going to learn a whole bunch more in the next couple sections. So apply trig identities. This is the second rule of thumb. You try the algebra first usually. Usually, it doesn't have to be. It's a clever trick, just use it. But common procedure, use algebra first and then apply trig identities to simplify it. And then C, if all else fails, right, you try rewriting the whole thing in terms of sine and cosine only. A lot of times this will just help you to see what to do. It was standing there in front of your face, but you couldn't tell before, right? If I saw 1 plus cotangent squared before, I might not know how to simplify that because I might not remember it's identity. But if I write in terms of sine and cosine, I'll come out of it in there with a sine squared plus cosine squared. Then I'll say, I know that one, right? So a lot of times, once you write in terms of sine and cosine, it's easier. Plus, it can reduce the number of trig functions. Whenever I see more than 2 trig functions in an expression, this is a thing I think of going to. If I reduce it to sine and cosine, now I've only got 2 trig functions. Maybe I'll see what to do. So whenever you have a lot of trig functions in here, or if you see these messy ones, tangent, cotangent, secant, cosecant, rewrite in terms of sine and cosine only using these reciprocal and quotient identities. So it's using identities again, but it's to reduce it, just rewrite in terms of sine and cosine only. Usually by the quotient and reciprocal identities that we just put up. That's it. It's just 3 steps. A lot of these things are just like the 3-step recovery programs. You got to keep it, not too many steps. But you can't. You got 27 steps. Nobody can remember, right? But 3 steps we can do. And now we'll just try these three steps for reducing some trig expressions, and you'd be surprised what we can already do, but we're gonna do more is the idea. It's a new trig identity. Just like algebra again, where there's too many identities. Still, they're really useful in other classes. And so let's say simplify each of these expressions. I'll give you some things similar to your homework here. Suppose this is 1a. Sine x times cosine x times secant x. How can I simplify that? See the trick? You might see it right off. If you see it right off, just do it, right? Well, maybe I don't see it right off. So I go to my rules of thumb, use algebra. Well, look, there's just three things multiplied together. There's nothing to simplify. I don't have canceling factors. It's mostly quotient theorems we're interested in. So there's really nothing to do with step, I should call this 1 here, so it doesn't look like ABC. Let's call this 1. It's problem 1A on your homework. All right, so I won't use part A, nothing to do, and then I'll go to B. Is there a trig identity I can pull right off? I don't see that in my list here, so maybe I go down to C. By part C, I'll rewrite this whenever I have more than 2 trig functions in here. I often try this. I'll rewrite it in terms of sine and cosine only. These are already sine and cosine, but secant by the reciprocal identity is 1 over cosine. Aha, now I see it, right? Now I go back to step A. The idea is you repeat all these things over and over until you're satisfied that it's simplified, right? So I go back to the top after I write it in terms of sine and cosine, back to algebra and say, now I've got it, because cosine cancels 1 over cosine. They're reciprocals, right? And this complicated expression just reduces to sine x. So that's an easy one, but it makes you appreciate the 3 rules there. You can just go through and try that until something simple. All right. I'm gonna look at D here. I'll call it 2. This is 1D. Suppose I had 1 plus tangent squared x of theta over cosecant squared theta plus sine squared theta plus 1 over secant theta squared theta. Now, some of these don't necessarily simplify, but the problem says they do. These are, here you're luckier than in real life, but still, it is true that a lot of times these expressions you get will simplify. Suppose I had to graph that one instead of graphing x sine x. How can I possibly graph this, right? What would I do? That's hard, right? But maybe I can simplify it and then I can figure out how to graph it. So, I mean, you put this on a machine and do it these days. You can even do it on your calculator in the graphing mode, right? That same graphing mode we use to sketch the shifted and stretched trig functions we can use to sketch these too. It's hard to know when you have the big picture on this. So these are kind of nice to simplify and then sketch. Well, what do I do with that? Again, I'll try algebra first. Do I see anything that cancels in these? Maybe I can put more of a common denominator. I could try that. This one could be sine squared. Doesn't look like it's going to make it simpler to do that. So I'm trying seeing if there's any trig identities I can use. What's a trig identity I can use? See anything there?
The 1 plus tan 2, no?
Yeah, 1 plus tangent squared was equal to secant squared. So I can write this equal to secant squared. This is by B. I can replace 1 plus tangent squared with secant squared. My x again. So that simplifies a little. So I've used A and I've used B. Now I'm on to C. Well, since I maybe don't see what to do, I rewrite it in terms of sine and cosine only. I'll write secant squared is 1 over cosine squared. Cosecant squared is 1 over sine squared. I've got plus sine squared, so this is by C. plus one over secant is one over cosine, so secant squared is one over cosine squared. Right? And now I've got it here. Now you repeat, you go back to A. Use your algebra techniques, and now they really apply. Here I have a compound quotient. What am I gonna do? Top times bottom over middle times middle. This is, can't read that, can you? Sine squared. Top times bottom is sine squared. Middle times middle is cosine squared. So I can write it like that. Sine squared over cosine squared. That's simpler. Then plus sine squared, that doesn't simplify with algebra. And then a reciprocal, you just turn the quotient upside down. So this is cosine squared. 1 over cosine squared is cosine squared. So that's by algebra A. So I simplify by algebra. Now I go back to B and I look at my identities again and see if I can simplify anything. Sine squared over cosine squared is tangent squared, but maybe I want to wait on that just a little bit. Sometimes it's hard to tell. Yeah, we can go ahead and write it. I don't think it'll help it that much, but let's write that as tangent squared. Sometimes the problem is if this doesn't simplify to something nice, then the next step I write in terms of sine and cosine only, and it puts it back. But let's put this as tangent squared plus, sine squared plus cosine squared is identity. That's 1. So by B, I can write that as tangent squared, and I can write that as 1. And now also by B, once I've done that, I can do a second time tangent squared plus 1 plus secant squared. I know exactly how to graph this. This was some horrifying mess with thought, but actually it's just a graph of secant squared. Put it up here. What you can do for that, really to get an accurate graph, you need your calculator or a computer. Computer's even better than calculator, but you can have a picture in your mind that gives you approximately, right? Here's what we remember about secant. Remember secant, it touches the cosine functions, peaks and valleys. So here's secant goes like that, where the cosine crosses the axis. Secant has an asymptote, so we look like that. So here's y equals secant x. What does secant squared x look like, do you think? Well, this is 1 here. Secant squared of 1 is still 1. So this point, 0, 1 is still 0, 1, right? I square 1 and I get 1. But if I square a bigger number, like here, maybe secant pi over 3, cosine is 1/2, and secant is 2. Then secant squared is 4, so it goes up steeper is what the idea is. You draw a U-shape up like this, but steeper. The bigger the numbers get here, their squares are even bigger still. So you have the same asymptote actually at, this is pi over 3, and the asymptote's at x equals pi over 2. Same asymptote, x equals pi over 2. But it's steeper because you still put it through 1, but over here, when you square 2, you get 4. When you square whatever this is, when it's 3 here, you're getting 9 here, and so forth. And now this part is just identical to this part, recall, but negative. So when you square it, it becomes positive, you get the same thing. So this one is also a steep curve, also going to go to 1. Your next asymptote here was at 3 pi over 2. Remember, these are odd multiples of pi over 2. You still have all the same asymptotes, but a steeper function, and all these ones that are down are now up. It looks just like these. So it looks like this. Steeper than that one, but U-shape up, U-shape up, U-shape up, right? So I can picture in my mind, thinking about it just a second, that this is what it's going to look like roughly. And a calculator or a computer can do a better job. So this section actually doesn't ask you to do any sketching. I just do this to show you some of the utility of this for your education, if you will. What you want to be able to do is these 3 steps, A, B, C, over and over. Get simpler expressions for reasons such as being able to graph, right? Or have an intuition. I know that by intuition, this is what it looks like. This is a circuit or something. I know some things that it's doing, like it's going off to, burn the circuit up if it gets high voltage. Anyway. All right, there's another. Okay, then the second thing we can do is to verify identities. Let me try and put this in a politically correct term, right? You don't want to use abrasive language when you're being a politician, so they don't want to say proof here. They say verify the identity, right? No, it means proof. I'll be a little more blunt. So we can verify identities. We can do proofs. We can prove some new theorems for trigonometry. How about that? And how are we going to do this? By using the same rules of thumb that we did for simplifying. Oh, my yellow chalk, should I? Same rules of thumb for simplifying. And what's more, since we have an equation, we can work from both sides. We can work both sides of the equation to a common middle ground. Like they used to do with the railroads, right? The railroad from the east and the railroad from the west would drive to the middle and they drive the golden spike down. Hey, complete your proof. Drive that spike to the same middle. That's the way a lot of people do proofs. Sometimes you get stuck going, from the beginning to the end. So you start at the end and go back towards the middle. You go, there it is. Right. So that's a common thing people do in proofs. Then they only have to be half as smart. So let's try one of those. But see, it's the same rules of thumb, just drive both ends. Right? And so it's not so bad. Let's try this one here. Verify or prove. Now you can make your own designer identity, I tell people, right? Once you can do all these things, but the idea is you memorize enough identities that when you need to get another one, you can prove it using these. That's the idea. Nobody can memorize them. There's an infinite number, right? But you memorize enough to be able to prove the others. Suppose I want to show that cosine, this is 4a on the homework, cosine x minus cosine cubed x equals cosine x times sine squared x. There is another rule that's in the book, if you read the book here, and that's in almost every trigonometry book that says there's some additional rules, an additional rule of thumb that typically you start from the more complicated side and try and reduce it. I don't find that to be as helpful as a lot of books do, but you might want to keep that rule in mind. Start with the more complicated side. I don't know if these look about the same complication here. Suppose I want to prove this is actually identity. There's too many to memorize. Is that really true? What you do is you write one side here. There are other ways to prove it. You can write a sequence of equivalent equations or something. You'll see that sometimes. But what most people do is they'll say, well, here's the two ends, and I'll work them towards a common middle. Now, one thing I know right off, this is another rule of thumb. You try and get the same, you try and put them over a common denominator if there's quotients. You try and get the same functions on each side. Here I notice these are all cosines, but here I have a sine. One thing you can do on these is use the Pythagorean identities to try and get the same trig functions. Like for instance, instead of working from this end towards this end, and maybe I don't know what to do, I might work this end towards this end and say, I need to get a lot of cosines. I'm going to replace sine squared using the Pythagorean identity. So this is a real common trick in these, with 1 minus cosine squared. Okay? So it's using the trig identity. Sine squared plus cosine squared equals 1 aggressively here. We simply rewrite from this by subtracting cosine squared. Equivalently, this identity is sine squared equals 1 minus cosine squared. That is subtracting cosine squared from each side. But you memorize this, that from this identity, you also know that sine squared can be replaced with 1 minus cosine squared at any time. Also, if you subtract cosine squared from both sides, you'll find that, or sine squared from both sides, you'll find that sine squared can be replaced with 1 minus cosine squared. Sorry to write tiny in the bottom. So this identity, think of it more generally, if sine squared is 1 minus cosine squared, did it again. Cosine squared is 1 minus sine squared. Excuse myself there. So you can replace either sine squared or cosine squared with 1 minus the other one squared is the nice thing from that Pythagorean identity. So using this identity, the Pythagorean identity, I'll replace sine squared with 1 minus cosine squared. Then you go back to your algebra tricks and multiply this out. Cosine times cosine is cosine, or cosine times 1 is cosine. Cosine times minus cosine squared is minus cosine cubed. Voila, I got it back. There we go. So working backwards on this one worked. Now I get to erase this step and say, aha, just multiply out and I get it. There's the spike. But that's the trick often is you use these identities, you simplify things by canceling common factors and putting them over a common denominator, so forth. You write it all in terms of sine and cosine, but also, also you gotta be a little more clever using the identities like that sometimes. So these, what you can see out of this is kind of like learning a sport. I remember the first time I tried ice skating, I was falling down the cliff, ice hurt, but when I went back, I'd done a lot of roller skating and it was easy. And so what you need to do is some sort of practice. If you can't ice skate, you practice roller skating. So these really take practice is what they take. Everybody knows the identities now, right? But you just have to learn to visualize. Oh, I can replace sine squared with 1 minus cosine squared. And then you got it. Right? So let's try another one here. I think I've got, let's see. Yeah, let's do one more. This will be the last problem. And then we'll have a nice. Verify the identity. Trying to make sure that's still on. That says, this time we'll start with the cosine squared x minus tangent squared x is equal to, not all of it, cosine squared minus tangent squared over. No, that's it. That's the wrong one. Is equal to all this stuff. 2 minus sine squared x minus secant squared x. Who would ever think this is actually true? But you can show that it's true. We think, well, let's see if it is true. How can we make the two ends meet? Again, you think about algebra, there's nothing to cancel in here. There's no compound quotients. So all those quotient theorems don't really do a whole lot for us. So we try trig identities. There might be one, if I'm real clever, I can probably figure out what to do with it. But sometimes it's hard to be real clever. So suppose I'm not real clever, just starting this up. What do? I go to step 3 and just rewrite everything in terms of sine and cosine, because maybe I don't see what to do. And that's a big help on these, is that sine and cosine rule, because look, I've got 1, 2, 3, 4 different trig functions. If I rewrite in terms of sine and cosine, I've only got 2. So let's try that. This is cosine squared minus sine squared over cosine squared, right? Tangent is sine over cosine, so tangent squared is sine squared over cosine squared. This is all in terms of sine and cosine going this way. And then I also go this way, and I write this one. This is 2 minus sine squared. And secant squared, I can write as 1 over cosine squared. Here we go. So if I'm not real clever, if I'm real clever, I can just say, oh, I see it immediately, and there's no steps, right? But if you're clever enough, but sometimes you're clever enough to see it in 2 steps or something, but try to write in terms of sine and cosine. Now I only have 2 trig functions to match up. How can I get this? It's not real obvious here, is it? But again, I use that rule. I want to get a sine squared here or a cosine squared here. What if I rewrote this as there's a lot of ways to go here, by the way. And on the test, what I want you to do is prove it And if you have the longest proof in the class, it's still right, you get 100%, right? It doesn't have to be short, it has to be true. So, don't worry about, being short necessarily. Sometimes just, do lots of steps, that's just as good. All right, well, look, I have a cosine squared here and I have a sine squared here. Maybe I can make them match. Let's try going down this way and I'll write sine squared is 1 minus cosine squared. Let's rewrite this. I hope I left enough room. Sometimes the problem is you don't leave enough room in the middle. Cosine squared minus 1 minus cosine squared over cosine squared. And I do that because then I'll get a 1 over cosine squared here that looks like this one. So you're trying to make these meet. And now I can break this one up into using your algebra rules. Say, this is minus 1 over cosine squared. That's good. That looks like that one. Minus a minus is plus. Cosine squared over cosine squared is 1, right? So this over this is minus minus. This over this is 1. Minus 1 over cosine squared is this one, and I carry that one down. Now it's starting to look a little better. Because I got the minus 1 over cosine squared matching. And now how can I make the rest of it match? Well, I can go different directions. I can replace sine squared here with 1 minus cosine squared, right? The Pythagorean identity. All right, so I'll just replace sine squared going up this way by the Pythagorean identity. Sine squared is 1 minus cosine squared. And now can I make it match? Yeah, we see it at this point. I drive a spike right here because I think you can see it here, right? Minus a minus cosine squared is cosine squared. That's that one. 2 minus 1 is 1, and here's my minus 1 over cosine squared. So they met in the middle. Okay, just enough room, I guess. You hope you get lucky at these things, but sometimes you have to put arrows over the side of the page. I understand that. Try not to do that because it's hard to read. But, there it is. I got the two ends to work towards the middle by converting all the sine and cosine and using my Pythagorean identities to rewrite these things. Those come up a lot, the Pythagorean identity. When you see a square, always think of that. I can replace sine squared with 1 minus cosine squared. I can replace 1 plus tangent squared with secant squared, right? I can replace 1 plus cotangent squared with cosecant squared. You can always do those kind of things to make it easier. All right, so that's the end of that one. Let me suggest in this homework over the break, 7.1, 1 through 4. All right. We have a quiz at the end of next week, right? At the end of next week, Thursday next week, what's going to happen? We're not going to meet again until Tuesday because of the holiday. On Thursday, we'll have a quiz 3 days after you get back. So work on these over the weekend, 7.1 and 7.5. 7.5 is really hard. So bring questions on Monday, maybe that you didn't have today, and we'll work on those. Ready for Thursday, hopefully, next week. And for now, then we'll do our quiz. I'm going to close it out on one.